Welcome students, welcome to today's session of All 4 e-learning. In this track, yesterday we have studied about the different types of expansions possible in case of solids. Just to make a quick review, depending upon the shape of the solid, we said that it can have linear expansion, areal and volume expansions. If the wire you have taken, suppose you have taken a solid in the form of a wire, the dominating length, the dominating property associated with this or the parameter is length. So because the volume and mass are negligible, area of cross section is also negligible, we cannot study the changes in volume and area, and because the length is large compared to volume and area, we can study the linear expansion. And if the body is a two-dimensional body like a metallic plate, then because of linear expansion along the length and breadth also, we said there will be an increase in area. That means in a two-dimensional body like this, we can study a linear expansion along the length and along the breadth also. So that leads to areal expansion. So we can study linear expansion in each direction and also the areal expansion, because area is also expanding. And finally, when you consider three-dimensional body like a cube, suppose there is a three-dimensional body in the form of a cube like this, then there will be a linear expansion along the height, length and breadth, so that linear expansion in all the three perpendicular directions produces an increase in area of each face. So for each face you can study about the increase in area or areal expansion, and as a whole in the body there will be an increase in the volume also. So we can study the volume expansion. Like this, depending upon the shape of the body, we can study linear, areal and volume expansions. Now coming to today's class, let us go for the measurements of these expansions. How to measure the expansion produced and what factors the expansion depends upon. So let us discuss about those things. Now consider the linear expansion first. Considering linear expansion. Linear expansion, under this heading we are studying an expansion in length, of the body. Consider a body in the form of a wire or a rod like this, whose length is L. Let us say the length is L1 at a low temperature, let us say some temperature T1 degrees centigrade, or you can say room temperature. The length of the body at a temperature T1 degrees centigrade is L1. Now suppose we are increasing the temperature. Because of increased temperature from T1 to T2, suppose the length of the body is slightly increased, and let us say the final length is L2 at the temperature T2 degrees centigrade. So L1 is initial length and L2 is the final length corresponding to a change of temperature from T1 to T2. So in this process, if you consider change in the length of the body, change in the length of the body is L2 minus L1. This is called expansion. This is known as linear expansion. So this linear expansion delta L is produced because of change in temperature. Now practically, by observations of practical experiment, we can understand that the change in the length of this body depends or directly proportional to the initial length. That means if the initial length is more, expansion is more. If initial length is less, the expansion or change in the length is less. Like that, it is a practically obtained result that change in the length of the body is directly proportional to initial length. And it is also proportional to change in the temperature. That means when the temperature increases large, when the change in temperature is very high, the expansion is also very high. When the change in temperature is less, a small amount, suppose the temperature is increased by 10 degrees centigrade only, the change in length is very small. Correspondingly, if the change in temperature is 100 degrees centigrade, clearly the change in temperature is made 10 times. Then change in elongation or change in the length also becomes 10 times. So clearly change in the length is directly proportional to change of the temperature. So there are two factors which influence change in the length of the body, that is length, original length or initial length, and change in temperature. Of course, there is one more important parameter which determines the change in the length, that is the nature of the material. Nature of the material, that is, suppose you take metals. There are so many metals like iron, copper, aluminum, etc. So many metals are there. Every metal has its own property. So because of that reason, all the metals, even though having same length, even though there is same change in temperature, do not expand equally. That means nature of the metal is also an important property which determines change in the length of the body. Mathematically, we can show that change in length depends upon these two factors, and from these two values, what we can say is change in the length is directly proportional to the product of initial length and also change in temperature, T2 minus T1. Then to equate this, to get the change in the length, let us consider a proportional constant here. To introduce an equality, we are introducing a proportionality constant. Otherwise, you can say delta L equal to L1 into alpha into the change in temperature, which is T2 minus T1. This is the change in temperature. And here alpha is the property related to the material of the wire. Remember, alpha is the property of material, not the wire. It is the property of the material of the wire. And this alpha, we call it as the coefficient of linear expansion. Coefficient of linear expansion. That means it is the factor which depends or which decides the change in the length when L value is same and change in temperature T2 minus T1 is also the same, because it is the property which depends upon the nature of the material. For example, you take four rods of different materials. Let us say iron, copper, zinc and aluminum. 4 rods I have taken, but all of them are having same length. For all of them, change in temperature is also the same. But what makes them to expand by different amounts is nothing but alpha. Because it is the property, coefficient of linear expansion, it is the property of the material. So different metals will have different values of coefficient of linear expansion. That's why even though initial length is same and change in the temperature is also the same, all different rods of same material, they do not expand equally because of this property. That is the property of the material, which we call it as coefficient of linear expansion. Now, how to get the value of coefficient of linear expansion? From this equation, if you say initial length is L, the change in the length we can write delta L is L of alpha of T2 minus T1. This is the equation for delta L, from which we can write alpha equal to delta L divided by L of T2 minus T1. That means what is delta L here? Change in the length L2 minus L1 divided by initial length L1 of T2 minus T1. This is the value of alpha. Then what is L value of L2 alpha? How to define this? This is the change in the length. This is the change in the length per unit original length. That means L2 minus L1 by L1, corresponding to the change in temperature equal to 1 degree centigrade. That means let us write here. From this equation, when T2 minus let us say delta L is L2 minus L1 divided by L1, when the change in temperature T2 minus T1, if you say that equal to 1 degree centigrade. When T2 minus T1 is exactly 1, delta L becomes L2 minus L1 by L1. This is very clearly ratio of change in the length to the original length. We can define as alpha. Let us define alpha. Alpha is the change in the length to the ratio of change in length to the original length, or change in length per unit original length corresponding to a change of temperature by 1 degree centigrade. So we can define alpha like this. I am repeating once again. Coefficient of linear expansion alpha can be defined as the ratio of change in the length to the original length corresponding to 1 degree centigrade change of temperature. Now we can also write this as alpha equal to, because change in length is delta L and original length is L, when change in temperature is 1 degree centigrade. So delta L by L for 1 degree centigrade, that is the value of alpha. Now taking the unit, how to give the unit of this alpha? Unit of alpha. Here we said change in temperature is already 1 and delta L by L is the value of alpha. When delta L and L, this is length and this is the change in the length. But we know length and change in length are measured in the same units. If L is in meter, delta L, change in the length, is also in meter. If L is in centimeter, change in length is also in centimeter. So practically, as the unit is cancelled, no unit is present for the value of alpha as per this equation. But because there is a change in temperature here, L and L are cancelled. But practically, because we have a temperature 1 degree centigrade, as these two are cancelled, even that because of change in temperature, we can say finally the change in temperature is per degree centigrade. Per 1 degree centigrade change of temperature, this is delta L by L. So unit of alpha we can explain as, if you are looking at delta L by L, for 1 degree centigrade change in temperature, it appears as there is no unit. But because there is 1 degree centigrade temperature is here, so which indicate that value, the unit of alpha is per degree centigrade or per degree Fahrenheit. We can explain like this. So unit of alpha per degree centigrade, we can express like this. Now suppose alpha of a material is given as suppose 2 into 10 power minus 5 per degree centigrade. That means when you are measuring the temperature in degree centigrade, we can express the value of alpha like this. But we know we can express the temperature either in Fahrenheit scale or centigrade scale. Generally we use these two scales frequently. Suppose I want the value of alpha in Fahrenheit. In Fahrenheit, you know that 1 degree centigrade you can write as 1 degree centigrade corresponds to 9 by 5 degrees of Fahrenheit. 9 by 5 degrees of Fahrenheit or 1.8 degree Fahrenheit. So when you are expressing the value in Fahrenheit scale, it is 2 into 10 power minus 5 per degree centigrade. Degree centigrade is nothing but 9 by 5 degree Fahrenheit. So very clearly it becomes a 5 by 9 value, 5 by 9 multiplied by 2 into 10 power minus 5 per degree Fahrenheit. So to get the value of alpha in Fahrenheit, we have to multiply the value in centigrade scale by the value 5 by 9. Because 1 degree centigrade increase of temperature corresponds to 1.8 degree or 9 by 5 degree centigrade rise of temperature in Fahrenheit. So corresponding to 1 degree Fahrenheit, that means the temperature increasing is very small when you measure in centigrade scale. So corresponding to that, the value of alpha will be small. So what is the relation between the value of alpha in centigrade and Fahrenheit scale? We can express from this equation. Now let me write here the relation in the two scales, because when you got the value of alpha in centigrade scale, multiply that with 5 by 9, you get the value in Fahrenheit scale. So alpha in Fahrenheit scale, that is 5 by 9 times of alpha in centigrade scale. We can express the relation between the two scales like this. Alpha, coefficient of linear expansion in Fahrenheit scale of temperature, is 5 by 9 times the value of alpha in centigrade scale. So this is how we can convert the values of alpha from one scale to another scale. Right. Now, after knowing this change in length and values of alpha, let us discuss about an important change in length. We have considered a rod of length L corresponding to a change in temperature delta T, that is T2 minus T1. Let me write delta T is T2 minus T1 and L1 is the initial length and final length is L2. So L2 minus L1 divided by L1 of change in temperature T2 minus T1. This we have defined as alpha. This we have defined as alpha. So L2 minus L1. L1 is the initial length, L2 is the final length. So change in length is L2 minus L1 and divided by the initial length and change in temperature. L2 minus L1 by L1 of T2 minus T1. This is the value of alpha we have defined. From this equation, let us get the final length. What is the final length of the rod? Let us calculate. So by cross multiplication you can say L2 minus L1 equal to L1 of alpha of T2 minus T1. Or taking the L1 other side, L2 becomes L1 plus L1 of alpha T2 minus T1, or you can say L2 equal to L1 of 1 plus alpha T2 minus T1. We can write the value of final length as per this equation. L2 is the final length of the rod. L1 is the initial length. T1, T2 are the initial and final temperatures. Then we can write L2 equal to L1 of 1 plus alpha T2 minus T1. Directly you can calculate the final length. In some problems we need this equation. L2 is L1 of 1 plus alpha T2 minus T1. This is one way. Now we can express the same in another way also. Corresponding to change in length, let us say L2 minus L1. Let us say it is delta L. And let us say initial length L1 is L. And change in temperature, let us say T2 minus T1 equal to delta T. Then what you will have? Alpha equal to delta L by L of delta T. Delta L equal to L of delta T. You can find out like this alpha. And change in the length also we can write L alpha delta T. And final length L2 equal to initial length L plus delta L. Change in the length. Final length I am writing like this. Initial length plus change in the length. So this is L plus change in the length is L alpha delta T, or you can express it as L of 1 plus alpha delta T. Here we are writing in absolute terms T1 and T2, T2 minus T1. Simply it is delta T here. And change in the length delta L we can express like this. So all these equations are similar. We can understand in any way regarding the change in the length. Now let us measure another related changes in the length corresponding to change in temperature in a body. What are they? Let us proceed with this equation. Change in the length delta L equal to L alpha delta T. As we know, this is the absolute change in the length. Absolute change in the length delta L is given by L alpha delta T. Now relative change or change in the length per unit length, change in the length per unit length or relative change in the length, that we can measure as alpha delta T. And let us also calculate percentage change. Relative change multiplied by 100, that gives the percentage change. So the percentage change in the length delta L by L into 100, we can measure it as alpha delta T into 100. So all these equations, delta L equal to L alpha delta T, and a relative change or fractional change delta L by L alpha delta T, and percentage change in the length delta L by L of 100, it is alpha delta T into 100. All these equations we have to remember as far as the problems or numericals are concerned. L alpha delta T into 100. Now listen, one important point that we have to note very carefully. What is that? If you observe the relative change in the length or percentage change in the length, relative change is alpha delta T and percentage change is alpha delta T to 100. Very clearly in both these equations we don't have the length. That means the relative change or fractional change and the percentage change, they do not depend upon the original length. They do not depend upon the original length. They depend only on change in temperature. They depend only on change in temperature. For example, I have taken a rod of length 1 meter. Initial length is 1 meter. and alpha, the coefficient of linear expansion is 5 into 10 power minus 6 per degree centigrade. And for this rod, I have changed the temperature delta T by 100 degrees centigrade. Then what is the fractional change? What is the fractional change? Let us calculate. Let us apply these equations which are useful here. I want the fractional change delta L by L. Let us calculate all these values. What is the change in the length? Delta L equal to L alpha delta T. What is length initially? 1 meter. Remember, when you are using the length in meter, the change in length also you will get in meter. If you want the change in length in centimeter, you can also take this initial length also in centimeter. So generally, we have to express all the answers in SI system. So let us take this 1 meter directly. So initial length is 1 meter and alpha is 5 into 10 power minus 6 L alpha. What is delta T? Delta T, the change in temperature is 100. So let us multiply with 100. Then the change in the length becomes 5 into 10 power minus 4 meter. 5 into 10 power minus 4 meter, because 10 square will be cancelled here. So change in the length of the rod is 5 into 10 power minus 4 meter. If you want in centimeter, you can also write it as 5 into 10 power minus 2 centimeter. So you can express in any way. Now let us move on to fractional change. Fractional change delta L by L. What is the fractional change? Alpha delta T. So it is alpha delta T. Alpha is 5 into 10 power minus 6 and change in temperature is 100. And we can say the relative change or fractional change is 5 into 10 power minus 4. And percentage change delta L by L into 100. Delta L by L into 100. That is delta L by L into 100 is 5 into 10 power minus 4 and percentage change multiplying with 100, it is 5 into 10 power minus 2. That is the percentage change. So we can calculate the change in length, fractional change in the length and percentage change in the length, all these things like this. This is a simple example to understand. Just to understand, this is a small example. Now let me try to understand another important point here, that is the percentage change is independent of the original length. Independent of the original length. That means if original length is 1 meter, you are getting the percentage change like this. Now suppose I will take the original length 2 meter. Let us see what happens. When I take the length as 2 meter, let us suppose length of the body is 2 meter. Now I am calculating these factors. That is the percentage change or fractional change delta L by L is alpha delta T. So even though initial length is changed, for the same change of temperature, if you observe alpha, the fractional change is alpha delta T. We can write as alpha is 5 into 10 power minus 6 and temperature change is 100. So it is 5 into 10 power minus 4. What is the value previously we got when length is 1 meter? When length is 1 meter, the fractional change is 5 into 10 power minus 4. But now we have taken a rod of length 2 meter. But even then, the percentage change is the same. And similarly, if you calculate the percentage change, delta L by L of 100, it is 5 into 10 power minus 4. The value of delta L by L multiplied by 100, again you will get 5 into 10 power minus 2, which is the same in the previous case where length is 1 meter. So remember that the fractional change and percentage change, they do not depend upon the original length of the body. They depend only on the values you can understand. Fractional change is alpha delta T and percentage change is alpha delta T multiplied by 100. That means they are depending on what factors? The percentage change and fractional change, they depend value of alpha and they depend upon change in temperature. That means material, what decides the percentage change or fractional change is the length of the nature of the material and the change in temperature. Change in temperature and material or nature of the material, these two are the things which decide the percentage change or the fractional change in case of linear expansion. So these factors we have to remember as far as the change in the length and fractional changes and percentage changes are concerned. But the important thing is percentage change and the fractional change, they do not depend upon the length of the body, but they depend on the nature of the material and delta T, the change in temperature. Now let us move on to the next expansion in area. As we studied previously, a linear expansion in two perpendicular directions produces an increase in area or an areal expansion. So corresponding to areal expansion, let us define a coefficient just like linear expansion. If once you understand everything about linear expansion, remaining coefficients of areal and volume expansions etc., they are very easy to understand because in the same lines we can think. Let us see how it is. Suppose there is a metallic plate whose area, let us say A1 at a temperature T1 degrees centigrade. Now because of increase in temperature from T1 to T2 degrees centigrade, as we said previously, there is a linear expansion in the length and also in breadth, so that the area is increasing. Let us say the final area is A2. Then if you observe the change in area A2 minus A1, it is a practically obtained result is that change in area is proportional to initial area. When initial area is more, change in area is also more. It is proportional to the initial area and it is also proportional to the change in temperature T2 minus T1. When temperature change is more, the areal expansion is also more. So it is the change in area is proportional to initial area and also change in temperature, or you can say change in area A2 minus A1 is equal to introduce a proportionality constant, we write a term beta. Beta of A1 of T2 minus T1, where this beta is called coefficient of areal expansion. Coefficient of areal expansion. So beta is the coefficient of areal expansion, and very clearly from this equation, beta we can write it as A2 minus A1 divided by the initial area A1 of T2 minus T1, the change in temperature. Coefficient of areal expansion beta, A2 minus A1 divided by A1 of T2 minus T1. Now how to define here? As in the previous case, if I take the change in temperature T2 minus T1 to be equal to 1 degree centigrade, then what will be the value of beta? It is A2 minus A1 divided by A1. What is that? A2 minus A1 is the change in area and A1 is the initial area. Therefore, we can define the coefficient of areal expansion as the ratio of change in area to the initial area corresponding to 1 degree centigrade increase in the temperature. Because we have changed the temperature by 1 degree centigrade. So, A2 minus A1 by A1, ratio of change in area to the initial area per 1 degree centigrade rise of temperature, that is known as coefficient of areal expansion. Or you can also say it is the beta, coefficient of linear expansion is change in area per unit original area per 1 degree centigrade rise of temperature. We can define in both the ways. It is the ratio of change in area to the original area per 1 degree centigrade rise of temperature, or it is the ratio, it is the change in area per unit original area per 1 degree centigrade rise of temperature. In any way we can define. And very clearly, as in the previous case, area, change in area and area will have the same units. Though these two units are cancelled. But remember, there is a change in temperature 1 degree centigrade. So the unit of beta is also per degree centigrade. The unit of beta is also per degree centigrade. So the unit of beta, similarly as we can write, it is per degree centigrade. Let us say have a numerical value 5 into 10 power minus 6 per degree centigrade, like this. So we can express beta like this. And again, in terms of the absolute values, we have written like this. And now suppose from this equation, if you want the final area, let us proceed as in the previous case to get the final area. That is, from this equation, change in area or A2 minus A1 is A1 of beta of T2 minus T1. And taking the value of A2 is A1 plus A1 of beta T2 minus T1, or you can say A1 of 1 plus beta of T2 minus T1. This is the equation for final area. Right. Final area is like this. A2 equal to A1 of 1 plus beta of T2 minus T1. So these are in the absolute terms, you can find out the final area. And now you can express in terms of the small changes. Let us say the initial area is A and change in area corresponding to a change in temperature delta T is delta A. Then very clearly delta A equal to initial area A and beta into change of temperature delta T. So delta A is A beta delta T, and if you consider the fractional change delta area by area, it is beta delta T, and percentage change if you consider delta A by A multiplied by 100, it is beta delta T multiplied by 100. So change in area, fractional change in area and percentage change in area, everything we can express like this in terms of changes, or in terms of absolute values also we have given previously like this. So we can measure beta in both the way, anyway like this. So in terms of this equation you can say beta equal to delta area by A of delta T. So change in area by original area per 1 degree centigrade rise of temperature. So we can understand in any way. So change in area is A beta delta T, and fractional change in area is beta delta T, and this is percentage change in area. Very clearly from these equations, as in the previous case of linear expansion, fractional change in area and percentage change in area both are independent of initial area. Whatever may be the initial area, fractional change and percentage change, very clearly from the equations, they do not depend upon the initial area. They depend only on the value of beta. That is, beta is also the property of material. Just like linear expansion, coefficient of areal expansion beta is also the property of the material, property of the metal, but not the property of the plate you have taken. Previously you have taken a plate, metallic plate. It will not depend, it is not the property of the plate, it is the property of material of the plate. So the percentage changes and fractional changes, they do not depend upon the initial area. Again, to convert the values of the beta from centigrade to Fahrenheit, because the per degree centigrade we are giving, we can express in a similar way, because centigrade degree we can write like 9 by 5 degree of Fahrenheit. So beta of Fahrenheit we can write like 5 by 9 of value of beta in centigrade scale. The relation between two coefficients remains the same as it is. Whether it is alpha or beta, to convert from CGS to the centigrade scale to Fahrenheit scale, we can use this relation. So either alpha or beta in Fahrenheit scale is 5 by 9 times of the corresponding value in centigrade scale. We can use this phenomena. Right. Let us stop our discussion today here, and in the next class we will discuss about volume expansion and applications of the linear expansions of the solid. Let us close here.